It's still good morning. Good morgen. Dzień dobry Państwu. So we start our panel discussion, which has the same title. Probably it won't. Is it better like that? No, better, because you know I don't want to have this reflection of the voice. Maybe like that. That's better. So we have this panel of limits of knowledge, and my name is Józef Spałek. I am a physicist by profession, and I'm from the Jagiellonian University located here in Kraków. And we have 4 distinguished speakers, and I presume that each of you will introduce yourself. That would be the best, Professor.
Okay, I'm a little bit surprised, but anyway, I'm Maciej Żylic, and I'm now president of the Foundation for Polish Science. By the education, I've finished physics and biology. I study also mathematics. I'm now working in the area very close to molecular medicine. And
that's it. Mm-hmm. Professor?
Maybe first of all, I would like to take the chance, since this is the last session, to say my gratitude to the organizers. This was a wonderful meeting, and I really enjoyed being here. So my name is Jürgen Heschler. I'm studied medicine, but I was always very much interested in physics and mathematics. So I went to physiology, and I got my habilitation, went to Berlin, and now to Cologne. Now I'm professor of neurophysiology, so I'm working on functional aspects of cells, but I work also for more than 30 years on stem cells. So this was my pioneering work, where we looked on pluripotent stem cells, which can develop in all cell types of our body, and we became very fascinated about this area in terms of how development of body of cells are taking place, how they can be used for regenerative aspects, and how they can be also used for testing methods. I was a coordinator of several big European consortia, and with this I'm happy to take part in this discussion in the stem cell aspects.
Thank you, Professor.
Yes, my name is Heinrich Wansing. I am a philosopher, and I used to work for more than a decade at the Technical University of Dresden, and then I moved to the Ruhr University of Bochum, where I am responsible for logic and epistemology. So I am a philosopher, but I'm not a very typical philosopher, I would say.
Okay, Doctor.
Good morning, and thank you very much for inviting me. I am humbled by this situation, being clearly the youngest, both of age and of academic age. My name is Łukasz Lamża. I am a philosopher, mostly dealing with philosophy of science and philosophy of nature. My home university right now is here in Kraków, the Pontifical University of John Paul II. And I am the associate of the Copernicus Center for Interdisciplinary Studies here in Kraków. Within philosophy of science, I would say that my main area of interest is cosmology and how cosmology demonstrates the limits of science. So this may be the reason I'm here, possibly. So thank you very much.
Okay, thank you. So you can see you have physicists, philosophers, and biologists, first of all. So we shall see how this mixture will work, okay? To introduce, to start with our discussion, I have prepared the fundamental questions about nature and about description of nature. The first of them, what is the source of life? Of course, none of the questions I am going to pose is possible to be answered in a direct manner, but still we will try. The second question is, what is the nature of our brain, of our mind? What is the nature of our intelligence or artificial intelligence? It's now being posed very frequently. And then, what is the structure or nature of our universe? Okay? And then there is a fourth question: what is the sense of our existence? And our famous philosopher Tadeusz Kotarbiński said that this is not a sensible question. Why? Because the sense of life is in our life, is in our existence, in our life itself. In Polish it sounds even better, but that's my poor translation. Okay, so that's how it is. And then I will, how to say, flash just 2 or 3 slides just to show you one additional unifying concept of that. And the 3 slides concern an evolution from atom to a biological system. As you know, every one of us knows that nature is composed of atoms, and probably not everyone knows that the smallest atom in the universe is not hydrogen atom, the simplest one, but the helium atom. And that's a very interesting question by itself, and the size of this atom is roughly 1 angstrom, which sets the so-called atomic state. Then, in physics, we always ask, how the nature changes as we scale the system, the increase the size of the system. Of course, this is not a Bohr atom, but actually it's a matter wave and so on. And then when we scale the system by order of magnitude, which means we go from 1 angstrom, okay, well, to 10 angstrom, which we set the scale, the unit at nanoscale, because it's nanometer, one part in 10 to 9 of meter. And then already, when we increase from 1 atom by 1 order of magnitude, the size of the system, we see that we can accommodate 60 atom structure, which in this case is fullerene, which composed of 60 atoms of carbon. This is actually the soccer ball. Oh yeah, okay. This is actually, as you probably know, zgasło, huh? Mehr Licht, huh? Okay, more stronger. So we have already 60 atoms. And now let's do the following. What happens if we no, it doesn't work. Okay. If we increase by order of magnitude, this is the slide which I have stolen from biologist, from Professor Magda Kosz-Wnęczak, who works in our Collegium Medicum, from her habilitation, and you can see that if we have 0.1 of nanometer, which is 1 angstrom, we have a size of atom or the size of a carbon bond, single bond. When we move by 1 order of magnitude to 1 nanometer, we have, of course, as I said, this fullerene, but also we have a glucose molecule C6H12O6. And when we move, surprise, surprise, when we move from 1 nanometer to 10 nanometers, suddenly, first biological system, the simplest viruses appear, and they range from 10 to 100 nanometers, which means the simplest one, which is probably mosaic, which is virus of the tobacco mosaic virus. I hope I'm doing it right. And I hope I'm doing it right. And you can see why I'm showing that. Because from 1 angstrom, from atom, we went only through 2 orders of magnitude. Suddenly, apart from the structure, function, biological function has shown, because the virus has the ability to adapt to the environment. And that's what we would like to do, to see in physics, this evolution in the exact manner. And I can tell you honestly, but what we can solve exactly in physics, with all these blue gene computers, it's exactly we can solve something like 16 to 18 atoms. So we are still far away from 1,000 or 2,000 atoms. And of course then all this plethora of the things will appear. So therefore, that's why we are here. And I'm showing the last slide of Philip Walter Anderson, the Nobel laureate. He's 93 and still going strong. If you write to him a sensible email, he will answer in 3-4 hours and scolding you mostly, because he's still going very strong. And he wrote a famous essay, More is different. More is different that we have a hierarchical structure of science, where biology is not physics, chemistry is not physics, biology is not chemistry, physiology is not biology, and so on. And I hope we will cover all these interdisciplinary subjects here. And now I should let speak Professor Maciej Żylicz, our president of the Foundation for Polish Science.
So maybe I would like to focus on the synthetic biology. This is something which is developing very fast now in the last 20, 30 years. And there are two things which are important. One is approach. One approach is to simplify already existing cell, living cell. And this is, we were doing this for the last maybe 50 years, trying to cut the genes and say, well, what is the minimum number of the genes which are required that this cell is still living? The definition of living, I would say that probably the philosophers should go after this. But anyway, so this is one approach. And this is what I'm saying, classical approach. I was involved also in this. I was able, after 20 years of work, reconstitute in vitro, it doesn't mean in a tube, the system which can initiate DNA replication. DNA is the information, have the information of the cell. And it took me 20 years, but I was using the enzymes which were existing in the living cells. I was just extracting these enzymes from those cells. And another approach, and this is the last 10, 20 years, is to try to build a living cell from scratch, from single amino acid, or even build a single amino acid from not using any enzymes. And next, using amino acids or nucleotides, build a bigger structure like DNA or protein. And this is actually, in the last 10 years, there's a big progress in this field. And it is possible to build without any enzymes the nucleotides. It's possible to build amino acids. And from those nucleotides, it is possible to replicate, well, replication maybe not, but to synthesize a small DNA without enzymes in the cell. Such an enzyme exists, is a polymerase, but without this enzyme, try to use a different approach. So this gives us, such an approach, gives us a hope that it will be possible to synthesize from the scratch a living cell. And this is, we are still hoping that this is possible. We did not succeed. It doesn't mean I'm not working exactly in this field, but a lot of groups, also in Germany, in Max Planck Institute, I am knowing few groups which are using the bubble, lipid bubble, and next put to this bubble nucleotides and see how fast and how efficient is the synthesis of the small piece of DNA. So this is where we are now, but the hope is like this. If this is a limit, I would say probably not. The limits are different. I would say the limits are in the beginning of not life, but in the beginning of Earth, and this is what I am seeing, these limits. But the evolution of the very primitive creatures to the living cell, we can, as a biologist, we can imagine that it is possible to how to say, to achieve this goal. Thank you.
Oh, thank you, Professor. I should mention that you can ask questions at any moment, interrupt us and so on, because I participate in such 2 panels, and we even quarreled in Gdańsk with some archaeologists and so on, and that was lovely. Fortunately, this was after banquet discussion, so people were somewhat relaxed and so on. Any questions? Any question at this point? Or somebody maybe wants to add something? Okay, if not, so we shall warm up. Okay, Professor Dubiel.
I would be happy if the members of the panel would answer the questions you posed. This, I think, would be very interesting, that everybody gives his idea about, yeah.
We do well, I said that the questions I posed are not answerable in a direct manner. I mentioned that, okay? So, listen. Maybe at the end, wait till the very end, okay?
This
Okay.
This was my plan actually, to answer all of them. So just
so
wait.
You see. Okay, go ahead.
Okay, so I have the difficult task to try to answer from the perspective of the stem cells. So maybe our question is similar what you say. How do life originates? So you start right from the scratch how molecules can adapt. So we are interested how our body is developing. During the embryogenesis, we know this is a miracle, so we cannot observe exactly how the things are assembling. But having these pluripotent stem cells, we are now, for the first time, I would say, able to get this knowledge, to cross the limits of knowledge, to understand embryonic development. And from this, we, first of all, are, again, I have to say, really fascinated that it's working. Even in a cell culture, if you just bring these stem cells together, if you assemble them, they start to organize themselves. And this is probably one of the very basic principles in nature. They assembling by themselves, they communicate by themselves, they secrete factors, and the factors are received, so we have a very, very complex information processing system, and we are just in the process to learn this, and this will be probably by getting the knowledge about the different signals, the different communications, we probably can cross our knowledge how cells can organize themselves to make tissue, or to make even a full body, or even to make a full human organ. The other point is, we can also do neuronal cells, and there are some colleagues working in the stem cell area to make the mini brains, so they call it mini brains, and this brings me maybe to your second question. What is intelligence? What can we say about intelligent systems? We also had a strong discussion in the stem cell area with the Catholic Church about ensoulment, and we really are asking the questions: is a brain just a network of nerves, as we heard, with intelligent brains simulated by computers? Can we simulate this? Or is a brain probably even something much more complex? We know, just looking in this early embryonic development, that cells can have very, very highly and very sensitive sensors, so they can probably sense single photons. They have a very, very high receptor activity, and the question always comes up: is our brain just working itself as a organ by itself, or does the brain works like a transceiver, receiving information from outside? And this the connection to the universe. This is also a question which is several times asked by biologists, isn't there more in our connections? Does our body works completely independent from other ones? Or do we have probably some signs that we get some other informations by physical signals which we don't have seen so far, that the brains can work together? And this is a question which also comes up in the stem cell area.
Thank you. I should mention that even in inorganic world, in physics, you have self-organization appearing as well. For example, you put atoms on a surface and they reassemble themselves, not just because they attract each other, but they form quite intricate pattern as well. So even atoms do some sort of self-organization. But my question would be to you, to both of you, is it understood these days, at the present time, that how stem cells become specific cells? Is this mechanism well understood already? Probably there are 2 or 3 Nobel Prizes already for that, but I would like to you to address this question in few sentences, if you can.
Yeah, I would say it's not so very bad. We don't work in the complete darkness. So we know for sure several receptors, several cytokines, several molecules which are interacting. So the general idea is that during the initial development, we have probably some very easy gradients, for example, oxygen gradient, or maybe even the gravity could play a role. So simple physical parameters which make a difference between different cells. And since we have in our DNA a lot of information stored, already a small difference between some cells makes some cells different to the other ones, and then some cells would start to secrete some factors, metabolic factors at the beginning, later more sophisticated cytokines, small peptides, and these molecules are then received by receptors, by the other ones, and so we have a transcellular communication, so the stem cells would communicate. Today we know several of these factors, so for example in the cardiac area we can add several factors to the stem cells, and then the cell would directly develop into the cardiac myocytes. If you look on the whole genome, maybe one should also say that, we assume we have around 40,000, maybe 50,000 plants of proteins. Proteins are the small machineries which are important for the cell function. And if we look on the cells, when they are starting to develop, they have a so-called housekeeping enzymes. This makes the cells just living, very primitive thing, and they are the same in all cells. And this is something like maybe 5,000 to 10,000 genes, enzymes, machineries, which are important in the cells. And then if you go to the specificity of the cells, if you go to a neuronal cell, or if you go to a cardiac cell, or if you go to a hair cell or eye cell, it's not so much. It's maybe only 1,000 genes which brings the cells to the specialization. So today, in the stem cell area, we think that the specialization is not maybe the very important physiological task. If you look back in the evolution, maybe it's a much more important thing for a cell is that the cell can multiply itself, and that the evolution goes on, gives the information to the next generation. So we see many more genes which are important for the self-renewal of cells, for giving the information further, keeping the information intact. So these housekeeping enzymes are probably even more important. At probably if you look at from the view of the evolution, our body is not more than just the way how the information has to be given from one generation to the next one. So it's a sophisticated machine to keep the information, because maybe in terms of the evolution, it's much more important to keep the information than to keep our body as an intelligent body. So maybe this is just a side effect of the evolution.
So it's not like in crystals that when you have a melt of this primary soup, you put just a small crystal light, and then boom, everything grows up immediately. Professor Szedzi, do you want to add something to this stem cell, specific cell difference? Or?
Well, we agree about how we are envisaged now the stem cell and the pluripotency of these cells. We are discussing as a biologist or people which are near the medicine also, how we can use these stem cells to regenerative medicine and things like this. And this is something which is still under very severe discussion. Of course, some people receive the Nobel Prizes to change the normal cells to the more pluripotent by special mutations. Now, in the last Nature, we read the article that this can be used to form the cancer. So the induced pluripotent stem cells, which give us a big hope to the regenerative medicine. Now this big hope is under big question mark.
Yeah. Okay. Thank you. Anybody has the question to that? If not, then we move further with the first round and move to philosophy.
Yes.
Professor Wanzing.
Yeah. Okay, when I was invited to this panel, I was a bit concerned, and I was wondering what could I possibly contribute to answering the question, Quo vadis science? And I soon realized that one can approach this question from a number of different perspectives and angles. And one, I think, is asking, so what are the big problems, the pressing unanswered questions, the main trends, and the great scientific challenges? And of course, these questions can be raised for each of the scientific disciplines, and I think we've seen that in almost every talk at this conference. So I vividly remember that in one of the talks here, the expectation was expressed that there will be a revolution in particle physics. I can answer this question only for my own field, of course, and this is philosophical logic. And there, indeed, there is a major trend that has been described by some as an informational turn or a dynamic turn. And the point is this. So philosophers used to be interested in notions such as belief, knowledge, desire, intention, obligation, and many other so-called propositional attitudes. But the modeling was mainly static. So they asked, what does it mean that an agent believes that phi? What does it mean that an agent intends that phi? And so on and so on. And then in the 1960s already, philosophers of science were interested in rational theory choice and in belief revision. And we heard a bit about this in the first talk today. And then a bit later in the 1980s, various formal theories of belief revision and dynamics have been developed. And the question now is, what does it mean to rationally revise a belief system in the light of new information? And that's the crucial term, information. Moreover, the notion of information has been crucial for the development of so-called non-classical logics. So there are systems of non-classical logic that deviate significantly from what is known as classical logic. And these investigations are partly driven by practical needs. So the information we receive and the beliefs we hold are normally, or at least frequently, unfortunately, inconsistent. So we all hold inconsistent beliefs, and we are confronted with inconsistent data. And classical logic would tell us to derive anything from inconsistent assumptions. Ex contradictione quodlibet. So it became clear that we need systems and models of inconsistency-tolerant reasoning and logics that allow for inconsistent but non-trivial theories. And let me also mention that one of the founding fathers of this field, which is now called para-consistent logic, was a Polish logician from Torun, Stanisław Jaśkowski. So in summary, I may say that there is a major trend in certain branches of philosophy. which might also guide the future developments there. And this is the logic of information processing and belief dynamics. So this is what I perceive as a major direction into which my field is developing. And I also believe that this reflects a more general development, because we're often said to live in an information age. And so I strongly believe that information is a central notion, not only in my field, but also in other fields, including biology and neuroscience. Yeah, thank you.
Thank you. Any question to that? Any question, any comment to the logical things and so on? I should say that since I am participating for the third time in this type of panel, I think that the Societas Humboldtianorum, they are doing it on purpose, that they do not ask people to prepare to the discussion, so they speak spontaneously and so on, and maybe something will erupt as the phoenix out of the ashes, okay? So don't worry to ask questions. The problem is, of course, with the answers, as usually. Yes, Professor, you wanted to communicate?
I'm always if you go to logic or mathematics, I'm always very fascinated. Do you think this is something which is in our nature, basically, and with this it comes also to the cells? And if I work with the stem cells, if we put together neural networks, do you think logic comes in a neural network? Or is it maybe something what we learn in our early life, in a school, that the brain just gets adapted to mathematical language, to questions? Or how is the link between physics and mathematics at the end? I guess in our brain we can imagine how the world looks in the physical area, and this corresponds to the nature. So I'm always fascinated about this thing, and the question is whether this can come also to biological system which we can grow maybe from stem cells.
Yeah, I would say we will return to the question of role of information. I read recently an essay in Nature, magazine Nature, that, for example, the laws of quantum mechanics, that just Schrödinger equation and so on, that it's just a theory of information, that this wave function does not have objective sense. And of course, then the question is what is matter, and so on. But that's the difference between information and material world somewhat in quantum mechanics gets blurred, if not smeared out. But that's another very important question. Okay.
Well, some philosophers and also some linguists indeed believe that there is an inventory of so-called innate ideas and innate concepts. And it's often emphasized that, for instance, the concept of negation, which plays a central role.
Concept of what?
Of negation.
Of negation. Oh.
Which also plays a central role in logic. That it is really a very, very fundamental and basic concept, because also for practical needs we have to make distinctions. We have to draw distinctions between things in our environment, and this brings us already very close to various concepts of negation.
Thank you. Yes? Okay. Question? Yes, please. Of course.
You mentioned inconsistent information, which should be somehow handled. Another trouble is when you look about applications is incomplete information. We see it very clearly in robotics. The information which comes to the robot from the sensors is very poor, and then classical logic doesn't help us too much.
Thank you. And to the lady. Okay.
Just a brief reply. I couldn't agree more. And so I mentioned this very strange term, para-consistent logic. There's a dual notion, para-complete. So, and you're absolutely right. It's not only that we have the problem of over-defined concepts. We also have the phenomenon of partiality and truth-value gaps. Yes.
Thank you. Okay, so Dr. Blamja.
Thank you. And actually decided in the middle of your talk to abandon what I wanted to say and say something
Very good.
slightly else.
Now you will say the truth.
Yeah, because I think that philosophy can actually, this is weird for many of you, I'm sure, can actually help a little bit in dealing with those 4 questions, because each of them is slightly different. But I would say that 2 of them, at least 2 of them, can be trivial in the epistemological sense. So let me just bear with me. If we are optimistic and believe that human race can progress in knowledge, we had a wonderful talk in the morning about that. Then let's say that we can know everything that is knowable, everything that is sensibly knowable. For instance, the structure of the human brain. Now, we heard another wonderful talk that it's one of the most complex entities in the known universe. Okay, but this is still a physical structure. And there is nothing in the structure of the universe itself that could stop us from knowing its composition, theoretically. Now, technically, it's very difficult. But theoretically, there's nothing that can stop us. So, for instance, right now there's the Human Connectome project that attempts to map all the connections between all the neurons of the human brain. So, if we are optimistic and we allow ourselves a little bit of science fiction, we can imagine that the human race has the full map of a model human brain, can model it in a computer, and it will help us understand the human brain. The same goes with the source of life. Life is a physical system. If we are not vitalists, if we don't believe in some sort of spirit in the bacterial cell, then we say, well, this is just a bunch of atoms. And we have seen the scale, we can do the math, 1 billion, maybe 1 billion atoms, but this is just a finite number. So at least I propose, this is my hypothesis, that we can at least all imagine that we have a computer simulation that starts with a simple non-living system. It goes through the laws of nature, and then we have a simple living system. So the theory of abiogenesis. Now the biologists study the details of that. For instance, was the first molecule, the informational molecule, was it DNA or maybe was it RNA? Were the enzymes actual protein enzymes or were they RNA enzymes, the ribozymes and so on? So I say the story is not trivial, but from the epistemological point of view, we can imagine it as a simple transition from state A to state B through laws of nature. So if you believe that life is just a lot of atoms, and if you believe that the human brain is just a lot of atoms, then I propose that you can believe that sometimes in the future we will have the full understanding of life and the human brain. Because there doesn't seem to be anything in the universe that could stop us from gaining this knowledge. Now, I would say that the third question is completely different, but let me just jump very quickly to the fourth one and say that there seem to be so many different answers to the fourth question, and at least one of them is the neo-positivist answer, that this is not really a question, that's not a well-formed question. It's a pseudo-question. It cannot be answered, in the sense that a good question is
essentially, Kotarbiński said that it's a tautology.
It doesn't make any sense, not even a tautology, because here mathematics is tautologies, right?
Yeah.
One is one, and therefore Pythagorean theorem and so on. So, but not even a tautology, just the terms are not well defined. So I'm not going to go into the fourth one because it's the most problematic, and I'm a lazy person, I want to go with the easy ones. So I would say questions 1 and 2, trivial questions, we just have to know everything that's knowable, right? Easy. Now, the fourth one, not a well-formed question, just leave it be. But the third one is related to my professional activity, because I'm dealing with philosophy of cosmology a lot. So just very quickly, you see, traditional physical cosmology is a normal science. It means that people who do it are normal people and they ask normal scientific questions. For examples, how are the galaxies located in the universe? What was the state of the universe 1 nanosecond after the time 0? Normal scientific questions, just like questions 1 and 2. But there are also the crazy cosmologists, people who say that science, the rational scientific method, can answer the ultimate questions. Where did everything come from? This is called the question of Leibniz. Why is there something rather than nothing? Why is there anything at all? Now this question, I would say, well, it doesn't seem like a physical scientific question, the type of 1 and 2. And yet those crazy people, they say, well, it's just a matter of time, more data, better equations, slightly better mathematics, and then we will be able to answer this question. Why is there something rather than nothing? Stephen Hawking in Grand Design says right there in print that science can now answer the Leibniz question. Now I would say that we have to go deeper than science, because if we ask why is there anything at all, we are begging the question, well, if I'm asking why is A, I guess I'm expecting an answer. So my answer will be because B. But if I'm getting an answer because B, well, my natural question will be why B? So someone will tell me, well, because of C. So I'm asking what? Why C? So I'm thinking that right now we're reaching to logic. We are leaving science, any rational method at all, because logic makes it impossible to answer question number 3, when it's asked in this very serious, crazy sense of let's answer everything. So, very quickly, answerable, answerable, unanswerable, unanswerable.
Okay.
Just to stir up the discussion, I guess.
Thank you. From the first part of your talk, I understood that everything is obvious, but of course we have in nature, in science, we have to ask the question first, how, before we ask why, right? And that's that we have some such thing like like great explosion at the beginning of the universe, and so that's the answer on how. And the fact that we can explain all other things like that, it's good enough for science. I have to tell you a story. Richard Feynman, when he was passing the entry exams in the graduate school at Princeton University, they had to write an essay in philosophy in order to pass the entry exams. And you know what he has written? He has written, I wonder why, I wonder why, I wonder why, I wonder. I wonder why, I wonder why, I wonder why, I wonder. And he passed the exam, okay? But that's Princeton, okay? Not Jagiellonian University. Okay, a question, okay? There is a question, okay, and the second one there. Okay, go ahead.
I don't have a question. I would like to say that the fourth question, what is the sense of our existence, is very well formulated. The key word in this question is our. What does it mean, our existence? If I understand the human being existence, then this will be a catastrophe. Because, as we know, the stability of life is based on the diversity. If we will progress in such a way as it was before, there will be a catastrophe, because people are trying to understand everything, even achievements of science to their own interest, pushing away everything, other forms of life from the earth. Now we are struggling with each other using nuclear energy. And I think this is the most important question of our existence. Our doesn't mean not people existence. life exists, and this is self-organization of molecule, and we only one form of this organization. We could speak more about this, but
of course, I meant our in the any sense you want to pick up. Okay, that's okay. Go ahead.
Can you really move along from the atoms? I think what you have to bear in mind is the emergence. The atoms are just modules. They have certain properties, and things are emerging from them.
Exactly.
Any of the scalar levels our chairman has shown in one of the slides is emergent from the previous ones. As you go scaling, and something extremely new comes up, and it is unexpected. We have so many rules. One of them is deterministic chaos, of course, but there are others teaching us that there is a development which is completely unexpected when you take the modules and think about something emerging on the scalar levels. One of the scalar levels would be the stem cells, or as we have tried to use it as a metaphor, we have called some species stem species, which can suddenly build up part of the biosphere. And the entire biosphere, according to the Gaia hypothesis of Lovelock, is one super organism. And again, it is unexpected. So I doubt I have problems with following you when you say you move on from the, or you can even use atomic particles and start a little earlier in the physical scaling up. And so what about, my basic questions are, it's now not there anymore, but it would apply to some of these basic questions we have asked, is the unpredictability and the emergence of something extremely new, which we only can observe after the self-assembly and self-organization has taken place, but we cannot predict it from the modules.
I love your comment. Why do I love it? Because when I graduated at university, I started teaching here at this college, engineers, physics. And then I go to the second Newton law, F equals m.a. And I said, oh gosh, how do I explain to them where it comes from? And then I realized that in physics, we are guessing the nature law. That's the difference with mathematics. It's an experimental science. And the philosophy of emergence absolutely helped me to understand what is not possible to explain rationally. And therefore, I will read to you what is the philosophy of emergence. The ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe in its whole complexity. The reductionist, which means physicist hypothesis, breaks down when confronted with the twin difficulties of scale and complexity, which appears with the scale. At each level of complexity, entirely new properties appear. Psychology is not applied biology, nor biology is applied chemistry. No, chemistry is part of physics. We can now see that the whole becomes not merely more, but very different from the sum of its part. And that's the article from Philip Anderson, where the title of the article is More is Different. So it's complexity. It's not only scale, but also complexity. And that's what I wanted to say. Okay, but we go, does it explain a bit with this motto of emergence? Yeah, okay, thank you. Okay, Professor Zilic, shall we move to the second round of our thing? Because then we move to another topic.
Yeah. Okay, so I was thinking that if we assume that the self-organization is possible, and next you have evolution, and evolution is created by the barriers of the evolution. It could be in a cell, it could be an oxygen. For cancer cell, we know how the cancer cells are working and things like this. But the barrier of the evolution could be different. So if you assume a stochastic process plus a possibility of organization, crystal are growing in such a way, and existence of the evolution barrier, you can end up in complication of the species, and you can end up with something which maybe we will define as a living cell. But I would say such a semi-linear, which is not a linear really, but it's a process, as you mentioned, it's simple. When we know everything, we don't know everything. This is why it's not simple. But I think we cannot apply this to the beginning of the universe. I was reading very carefully Haller papers, and he assumes that the self-organization is possible. But next, there was a few coincidences during the creation of the universe, and let's say creation of the oxygen, a very unusual situation. So we cannot, I would say, explain by simple models all these coincidences which were existing in the beginning of the universe. And my question is actually to the cosmologists. Maybe I do not understand because my knowledge is very limited, but maybe the cosmologists understand those coincidences which actually were important in the end to create the living cells, oxygen, and things like this.
Well, I started at a very general level of epistemology, what is theoretically knowable. But in practice, these things may not be knowable. So for instance, just lower. All right, excellent. Is it not too loud now? Okay.
It's okay.
For instance, in evolutionary biology, the theory is more or less known, but you cannot predict that there will be an asteroid collision 65 million years ago that will eradicate most dinosaurs and allow the evolutionary radiation of mammals, because it's not part of evolutionary theory. And even within planetary science, you could argue that it's actually impossible to predict because of deterministic chaos, that this particular asteroid will hit Earth at this specific angle on the Yucatan Peninsula and allow the evolution of our dear selves. So this means that this is in practice unpredictable. But what I meant is, if we assume full knowledge, so if we start with the description of the location of each atom, including the asteroid, on the proper trajectory, then theoretically we should be able to project into the future and understand why it all happened. But it's just in theory, in very, very coarse theory, because in practice the world is indeterministic, right? So the role of coincidences, I wouldn't say it's limited to the Big Bang and the anthropic coincidences you mentioned, the formation of a carbon atom and so on. But I mean the evolution of our planetary system, just a bunch of coincidences. The Earth has the moon because there was a collision at the proper trajectory, and now we have the moon. And now we have the tides, and we have the intertidal zones where evolution of life is multiplied. So there's just a bunch of coincidences, right? Mm-hmm. I don't know if they can be known even in principle.
I think for me what is important, in which manner we differ, is that the ability, what you just said, that we understand how moon was created and so on, this is the essence of science. That's good enough, I would say. Some of the other questions are senseless. You start from this, I wonder why I wonder, this is a basis, and ask more particular questions. I would probably allow now Professor Wanzing to say, because he has to leave sharply at noon, so maybe you would like to say something, what you want to say, and then we can prolong if the discussion is still going on.
Well, at this point of the discussion, I'm afraid I don't have to say much. I mean, you just were talking about failure of knowability in practice. And, well, I would like to point out that there is also failure of knowability in principle. which need not disencourage us as scientists, but we, as a matter of fact, I think have to acknowledge it, that there is, for instance, no complete finite axiomatization of piano arithmetic. So there are impossibility results, which are, as mathematical results, something we have to accept. As to the question of what is the sense of the meaning of life and the meaning of our life, I would agree. This is this question is difficult to answer because while some of the terms are not precisely defined, and I'm not so much concerned about the talking about our life, but about the meaning of meaning, that is the meaning of sense. And so this has to be made precise, and it's well probably very difficult to do that.
Thank you. Any questions? Any comments from the audience? And so on. For example, I would say I disagree to a certain extent with you philosophers, because you always ask as there is no end to asking. You have to stop somewhere. You know, we mathematicians or physicists say, oh, this is mathematics. This is, you know, this is mathematics. It is together. Everything must be based and quantitatively checked. Then this is, in my view, knowledge, not everything. Einstein said, it's a beautiful saying, I think I wrote to you in an email, that the physics, I mean, well, I would say science, is neither pure empiria, because it would be completely blind, nor pure theory, because it would be fruitless. It's the constant confrontation, what we observe with what we observe quantitatively, with what we think about that. And this is what is essence of science. We cannot question with the words only ad infinitum, because then sooner or later, you know, Occam razor should start working. So in this sense, I prefer doing science and having something like emergent phenomena, philosophy of emergence, rather than starting from science and then doing philosophy, rather than vice versa, starting from philosophy and trying to explain science. Because I think that's a blind road, but you may disagree with that. Okay. Yes, one more.
I have a question to the philosophers, and perhaps to all of us. The Viennese philosopher Lisman has written very emphatically, we need to distinguish three things. One is information. These are the atoms, these are the modules. From there, we move to knowledge. But this is not enough, and this is now my question to the philosophers. He has said, from knowledge we need to move to understanding. So what in your view is the difference, or is there a difference?
Very good, very good. Okay, who wants to answer that?
Just very quickly, there's this traditional definition of knowledge, which is justified true belief. And all of the three conditions have to be met for there to be knowledge. It has to be not only, well, I have to actually entertain it as a belief. It has to be true, but it's not enough. It has to be well justified. And this is, by the way, this sets a very hard limit for knowledge. Because it's not only that I say something and it happens to be true, I also need to have it justified. So for instance, in science, something has to be observable. That's the gold standard of science. Something has to be observable because it will give me the justification. So in case of theory versus observation, Einstein's equations predict or may be used to generate a model like a Schwarzschild model called a black hole model. And this is the piece of theory. Now, the moment when you start observing something, then you can say, well, now I have knowledge that these things actually exist, right? But the interesting question is, and I may ping-pong the question, if the inside of the black hole, technically the volume inside the event horizon, is unobservable in theory, meaning it is the causal structure of the universe in the sense of Hawking and Ellis. The causal structure of the relativistic theory makes it impossible for any signal to travel from the inside of the event horizon to the outside. Does it mean that this is outside knowledge? It would seem so.
Okay, I will answer that, but probably I should allow. Oh, you wanted to still, and then another biologist, because biologists should stick with physicists and forget about philosophers. Okay. Okay. After the, is it okay?
I would like to make a short addition to what you just said. In epistemology, there's also the notion of epistemic luck. So if you happen to have true beliefs, you can be lucky because what you believe is true, but in order to obtain understanding, and that was your question, we would require more. We would require that you are able to give a justification. And well, then we indeed end up with a classical definition of knowledge as justified true belief, but philosophy wouldn't be philosophy if this definition would not be under dispute. So the definition has been challenged since the early 60s when people came up with supposed counterexamples to it. But basically, I think you're right. We would require more than just true beliefs. We would want to have knowledge in the sense of understanding, which would imply, yes, being able to justify our beliefs.
Okay, probably the lady now. Where is the microphone? Mike. Sorry. So then, I'm sorry.
As a physicist, maybe I would like to address a very basic question. We have emergence, everything is emerging, biology from chemistry, chemistry from physics, physics from the elementary laws of nature. But the question basically is, where do the laws of nature come from? That's maybe the basic question which is fundamentally limiting our knowledge, which at the same time keeps us curious and keeps us humble at the same time. We have a set of laws of nature. If we would not have that, we would not have anything. Basically, everything is spanned out, derived, and made possible because the universe is following a certain set of nature, a certain set of laws which no one of us has made and which fundamentally cannot be explained but just observed and found.
Very good. Just a moment, the lady asks question because.
I of course agree that it is not so easy to define the meaning of the term sense. Nevertheless, I think we should not abandon it. And I would like to. Sorry, I would
a little bit lower. That's okay.
Excuse me.
No problem.
I would like to refer to a historical example from the history of philosophy. Well, I'm not a philosopher, but please allow me to refer to that. In 1936, Husserl published the first part of his famous The Crisis of European Sciences. And, well, I'm proud to say that first part of his crisis was published in a journal in Belgrade. Unfortunately, this was the consequence of the conditions in Germany at that time. But there, Husserl asked the question, how is it possible that in spite of progress of science and remarkable progress of science, the sciences cannot offer any help to human beings to answer the most important questions, and those questions are exactly the questions of the sense of life. So
that's the question they did ask there.
Yes. So I mean, in this Husserl's question, I see a necessity to relate the natural sciences. He obviously had in mind natural sciences and the questions of the sense of human existence. So it's our task to try to answer that question and to make sciences a tool which could help human beings to answer also questions which are not defined in precise terms. Thank you.
I'm a little bit disappointed that this discussion turned from those concrete questions to the what is science, what is the nature of knowledge, and so on. But I think you wanted to still to make short comment, a brief comment,
Very-
because
30 seconds. 30 seconds. About the gentleman's comment about the laws of nature and the source. Actually, I think that we can't go further than Aristotle did. He analyzed it very clearly. If I demand an answer to all my questions, if I want a justification to my question, then there are two options. One, I will have an endless chain of answers, and it's actually endless. So each new answer has a new question and so on. Or there's option number two. There's an answer that I don't question, right? There's something, this is the first principle.
oh,
This
there
is
is
something
first possibility
This is
to ask sensible.
so certain and so nice, and we are so confident in it that we don't question it. But there's only these two options, logically.
Okay.
So I would say this is a very hard limit for knowledge. One, we have an endless chain. Two, we have something we don't question. Right?
Maybe now move back to biology, okay, to
Yeah,
natural
I
sciences, okay?
have the feelings that now it
Yes,
moves too
and
much
then
into
Professor
physics.
Żylic will recapitulate.
Yeah, no, I think maybe I should also make more statements from the biology, and I guess it came to the point we probably all agree that information-rich systems, complex systems, is a nature where we generate our knowledge from, and from our brain, from our body, from the stem cells who are developing. And my point is this really something which can be derived through physical, mathematical methods? Just a simple point, when we are doing experiments in biology, I guess they are different to experiments as you do in the physics. I guess you really expect always a reproducibility. You can have 100%.
Not always.
Okay. But if we go to biological systems, if we go to our stem cells when they are developing, we can try to reproduce, but we see very often things are not reproducible. The cells behave differently. They have a lot of degrees of freedom where they can develop, and I guess this is linked to their very high information-rich systems because they probably don't need necessarily to be obliged to basic physical laws. I guess if we have a complex systems, they generate their own laws.
Emergent laws.
Yeah, maybe we heard this chaos theory and attractor theory. Complex systems. I guess these are probably some super laws which are based on natural laws, but maybe they give the cells more freedom. And my question, which I would like to raise, is that our systems. Therefore, I ask the question: is logic something which is always there? Is the mathematics is a logical system? How we are trying to answer questions, how we are trying to explain the nature, is this probably the only way how things can be described. So if I go to cells, I see probably a different systems. We have enzymes, and we have all enzymes going in feedback loops. So everything corresponds with everything. So if you take into account, I mentioned we have around maybe 10,000 enzymes. These enzymes are expressed in a cell, several billions of enzymes, and all these enzymes can interact with everything. So it's a very, very complex system, and this is what we call the swarm theory, that maybe by just copying things and bringing things in feedback loops to novel things. So maybe this can also be a way how nature is approaching description of the environment, and the point is if we really adapt to the mathematical system, if we try to use our physical way of thinking, are we really able to understand biological phenomena?
Thank you. Before I give the mic to Professor Żylic, I would like to make another anecdote. There was a famous mathematician living in Kraków here, Professor Stanisław Wojasiewicz, who died recently, recently 10 years ago or so. He was a member of this Nicola Bourbaki school, which reformed whole mathematics. And then I turned to Professor Wojasiewicz. I say, Professor, I have a problem. Why mathematics is so effective in physics and in biology? Because, you know, this is just a construct of brains. Where is this experiment in mathematics? And he says, it's in the jakie założenia, it's the assumptions of the theory. There is the ingenious, simplest type of experiment, like counting fingers, 1, 2, 3, 5, which is the source of arithmetics and so on. So mathematics has also this Grundlagen, has this basis in logic, in real life, in experiment, and so on. And that's essentially the thing. So I would stick to science, to this criterion of falsifiability of theory by Karl Popper, another philosopher from Wiener Kreis, who said that theory, you cannot always prove that theory is right, you can only prove that theory is wrong. If you propose experiment on the basis of which you could kill the theory, given theory, and this experiment fails, that's the test of falsifiability. And let's stick in science to that. But I think you wanted to ask something, and then Professor Żylic.
I wanted to make an input to this question our dear colleague from Serbia was posing. There's a deeply intriguing question. Can science contribute to your fourth question there? And it was Victor von Weizsäcker who gave some lectures in the early 20th century. I think it was in 1919 in Berlin. And he said and wrote, I say it in German and try to translate, das ist die Tragödie der Biologie. Jeder Fortschritt, den sie in ihrer Forschung macht, ist ein Nagel mehr zum Sarge des Verstehens, was das Leben ist. So, in a brief translation, every little progress this biological science is making is a nail on a coffin of understanding the sense. It is your important last question, and it is what you very nicely commented on. Can science really contribute to this?
Thank you. Now, Professor Żylic, do you want to?
I hope it's working. Yeah. I just want to say that answer your question, trying to answer your question. I think science is possible using a scientific approach. It is possible to predict the past, but it is very difficult to predict the future. And even if we biologists try to predict the future and saying something reasonable about the vaccines, there are a lot of people which don't think that vaccines are good and they are against this. So this is our limitations as a scientist. Thank you.
Yeah. Okay, thank you.
Yeah.
Just a moment, maybe from the audience again.
I would like just to say one sentence concerning the sense of life. I think that the life had or has sense as long as people do believe in God. And it was a case before the science has emerged. In the course of science, I think more and more people have started to have some doubts. And I think that the science makes that we do not believe in the sense of life, somehow.
I see. Mm-hmm. Well, Kotarbiński, who was, as you know, a famous atheist, he said that the sense of life is in life itself. Yeah. And I probably should add one more sentence. He said we shouldn't ask we should not have asked what is the sense of life, but instead we should ask what to do and not what to do. As you know, he was a creator of the philosophy branch, which was called praxeology. That was he called it science about the practical and the proper action, the practical action. Okay, the lady there.
I just have a small appeal for being open-minded.
Little bit higher.
We have to be open-minded because there is interconnectedness between things, between us, between sentient things, between non-sentient things. If you think about it, we are children of the stars, because if you look at our composition, we have all the atoms which are all over the place, and that's why I also think the hypothesis of Gaia, which to great extent takes into account how we are interconnected and what are the feedbacks, is one which we don't need to believe into God, we don't need to believe into anything, we just have to realize that we are interconnected.
Okay, so what we should, I have prepared, oh yeah, okay, next one, because ultimately the audience is the most important part.
I will present two short remarks. First will be connected with the main topic of the discussion. So I start with an anecdote. One eminent scientist had a lecture about Big Bang. And in conclusion, he concluded, we know all what's happened, for example, 10 to minus 44 seconds after. But he's intrigued what's happened during the Big Bang and the short time after. And he told that we connect all our forces to explain it. And somebody from the audience asked him, why? This problem. So he thought in the night about, was asleep, and at least he had a terrible dream, being awake, look around, darkness. He analyzed the situation and cried, oh, is a litany of non-parliamentary words, and we are one small 10 to minus 44 seconds before Big Bang. So why I tell it? Because the limits, borders are very relative. We create these borders, but because of progress in science and use of our brains, we can crush it. Second remark is to the existence. As yet, there's no good explanation. Maybe the explanation is the fact of existence. Sense and fact, maybe. But I think
but that's what I said in this my thing in the beginning.
And the best, maybe, let us have it in our privacy, maybe. Thank you.
Before we finish, I would like to quote certain things, and you know why. There has been a book published in Polish recently by Andrea Wolf. The original title is The Invention of Nature, The Adventures of Alexander von Humboldt and the Lost Hero of Science. And then I will quote about him, because this is very, very important thing. Unfortunately, I have only Polish translation, so I have to translate it back to the English, okay? Okay. So, we have been, the author writes, we have been formed by the past. That's what you said, past, not future. That's very good. Was Nicholas Copernicus showed us our place in the universe. Isaac Newton explained the laws of nature. Thomas Jefferson left us with his concept of freedom and democracy. And Charles Darwin proved that all the species originate from the common origin, common original ancestors. Those ideas defined our relation to the world. And then about Humboldt. Humboldt provided us with the concept of nature itself. It's irony that the Humboldt's views are so obvious that all of us have forgotten who has created them. However, there exists an immediate, a direct connection with him, with Humboldt, through his ideas and through the people whom he has inspired, like a rope, like a line concept of nature. Humboldt concept of nature is intimately connected with what connects us all. Okay, so that's about Humboldt. Okay, so now we have reached almost, we exhausted our time because it's exactly noon. We started 5 minutes early, so probably the last word by each of the speakers. If you want to summarize in one sentence, or if you want to, because you are as important as they are. Magic.
Well, so maybe I will be the last, because I usually was first. So.
Oh, I see. Okay, so let's go from the other side.
I don't have any very smart thoughts, so just a comment that I wanted to say anyway. We know we can predict the past so well only because we know it. Now, because we could run the simulations 100 times and tweak all the parameters. So there's no secret that science can predict the past. We just know it. All we have to do is just create a program that will create the curve that we already know, right?
That should be there.
If we knew the future, we could predict the future, right? But it wouldn't be any prediction at all. So this is my thought. Thank you.
Okay.
Okay, my final sentence. Maybe it's helpful in some discussions to point to a certain difference, the difference between knowledge and certainty. So it may happen that we know, but just as a matter of fact, we do not know that we know, which might also point to another limit of knowledge. Thank you.
So back to Socrates. Huh?
Yeah, I guess we had a good discussion on the first three of your questions: the sense of life, the intelligence, and the universe. For me, the conclusion is information-rich systems. That was for me an important point. The question: can we really describe things in this complexity? But maybe a point concerning your last point, the nature of our existence. Probably we really should follow Alexander von Humboldt. I guess he went out to other countries, and if we translate this in our time today, probably our planet is not enough to get an understanding. So today, several planets have been discovered which are similar to our Earth. And I guess there's no doubt life is probably also developing on other planets, and probably we really have to go out, like Alexander von Humboldt, to try to come to other planets, to see other life, extraterrestrial life, and probably then we will be able to answer why do we exist in this universe.
Yeah, that would be wonderful if the life was discovered on another planet. Wonderful.
Well, the last thought is about this self-organization. Of course, in the case of self-organization, you can get and reach something unpredictable, as you mentioned. But of course, we assume that during this time, all the law like thermodynamics and the minimum of reaching the minimum of energy and single supply. Of course, we know that there could be a lot of several local minimums, and you have a diversity of these self-organizations which can even go and reach the living cell, creation of the living cells. But one thing which is totally unpredictable and without any applying of our classical law is this first time after Big Bang, where the physical law do not apply. And this is something which is a miracle, or is something which we do not understand. And I assume that we will never understand this. And going back to the to the big question of all this meeting is that you can approach to the knowledge or reality, but you will never can reach the 100% sure that you know everything. So asymptotically you can approach to this situation, but you can never reach this.
Okay, so tempus elapsum est, as we would say. Our time is up. Thank you very much for taking things, and thanks, first of all, our panelists. Thank you.